Hi, Sweet Green class. I am so sorry about the technological difficulties and the Zoom crash that happened today. So I want to quickly go through what you missed so that you're caught up. So hopefully you can find 10 minutes or so to watch this. These are models of the atom that came off of Class Kick, actually from the other class, because the crash happened when I was attempting to pull yours in. So we're going to come back to these periodically and talk a little bit more about them. So I just wanted you to kind of have a view of them at this point. And our main topic for the day is Dalton's atomic theory. So the year is 1800. You're never going to be asked to spit back dates or even names of the scientists. But the year is around 1800. And John Dalton, who was actually a teacher as well as being a scientist, and Dalton compiled evidence that was available at the time. Now think about how you compile evidence back in 1800, right? You don't just send it over email. You can't just get on a plane and, go to a conference. So the scientific community and the communication was a lot smaller and a lot tougher to do, but still he compiled evidence in 5 points. The first of which was all matter is composed of atoms. And again, you're going to say, yeah, no kidding. I know that. Well, right, because you've grown up with this being widely accepted. At the time, this was a pretty big deal because there was hundreds of years prior, there was a pretty popular philosopher named Aristotle who contested this and said, no, I don't believe in, quote, the atom, or that concept, which is something Democritus, another philosopher, said. Aristotle instead said that matter was continuous and there wasn't kind of a smallest piece of it, which leads me to the next one, which is that atoms are indivisible. So indivisible means that they can't be broken down. Another way of saying that is atoms are the smallest part of matter. Okay, again, I'm not saying this remained what was believed, but at the time, this was what Dalton compiled. A third point is that atoms of a given element are identical to one another. And then conversely, atoms of different elements differ in their properties. So when I was in high school, I remember my high school chemistry teacher, Mr. Holinsky, was going over Dalton's atomic theory, and he told us this information, and I remember kind of scoffing and being like, well, duh. But again, you have to take yourself back to before or when scientists were just starting to kind of verify these discoveries. And then there's also something kind of ironic about me scoffing at this and saying duh, which we'll talk about later. Something else that found its way into Dalton's atomic theory is this statement. Atoms cannot be created or destroyed, but they can be rearranged. In what we call a chemical reaction. So we've been saying chemical change, but for the rest of the time, we're pretty much going to call those chemical reactions. So this statement, atoms cannot be created or destroyed, that is known as the law of conservation of matter. And you should know that. Law of conservation of matter, Dalton didn't discover that. That was someone by the name of Antoine Lavoisier. But he thought it was important enough to include in his atomic theory. So you can either say matter or atoms cannot be created or destroyed. You can also say it like this, and you should know both ways. You can say mass of the reactants in a chemical reaction must equal the mass of the products. In a chemical reaction, reactants are your starting substances. So there's a vocabulary term for you, reactants. And products are your end result of a chemical reaction. And the mass of the reactants of what you start with has to equal the mass of what you end up with because matter can't be created or destroyed. Last point in Dalton's atomic theory. Atoms combine in small whole number ratios to form compounds. And this was an expression of another law. And that law was developed by Joseph Proust, and it's the law of definite proportions. And the law of definite proportions states that a compound always contains the same elements in the same ratio by mass. So compounds contain the same elements in the same ratio by mass. So on your class kick, the answer here, regardless of what you put, the answer here is false. When a log burns, okay, you have a log. In order for burning, you also need oxygen. Your log, incidentally, is made up of carbon, hydrogen, and oxygen mostly. There are probably some impurities. You're going to get lots of stuff, but it's mainly going to be carbon dioxide and water and a little carbon monoxide and some unburned carbon, which you'll see is like the smoke dust and the ash, and then a few other impurities. But the bottom line is you can't just mass your log and then mass the pile of ash and say, oh yeah, we lost some mass. No, you would have to develop an experiment that masses the log and all the oxygen combined with it, and then that masses all your gases, all your smoke that's released. And if you could do that well and control your variables, then you would have masses that matched according to the law of conservation of matter. So I want you to read through this problem, ultimately answer if A and B are the same substance, defending your choice. Okay, so pause the video, work this out, and then resume. So there are multiple approaches, but here I compared the ratio of carbon mass to oxygen mass in each element, in each compound. So in compound A, the ratio of carbon to oxygen by mass is 0.374. And in compound B, it's 0.376. So in class, we had a good discussion that amounted to, hey, are these the same or are they different? Well, remember, guys, this is data. So there's always going to be some error in data, and there's no hard and fast rule on how much error is allowable. But I'm going to go with these are the same, right? They are absolutely, we can defend our choice that A and B are the same substance because they do have the same ratio of elements by mass. And then I'll just leave you with this quotation that was from your class kick, which is a good lead-in to your project, your Scientist Like Me project, which hopefully during the actual class time you got to read and just write down any questions you want me to answer about the project tomorrow. And then you can watch this video in place of your homework. But I really do want to try to be representative of all of the people who contribute to a scientific community, even the ones that maybe aren't recognized or weren't recognized in the past.